Welcome to another wacky, wavy, inflatable arm flailing physics problem. This is the rotated frame problem, in which we explore the forces that are acting upon an object when we are on a rotated axis. So, here we have a standard problem for this type of question. A 500-pound polar bear is sliding down a frozen 30-degree hill. The coefficient of friction between the hill and the bear's paws is 0.2. Things that we want to find are the normal force, the friction force, the net force, and the acceleration on the bear. And if we had to modify the problem, how could we modify the angle of the hill so that it would cause the bear to have 0 newtons of net force? So, first thing that we want to do before we answer any of these questions is to create a free body diagram. So what we want to do is just set up a box to represent the bear. And here's our 30-degree incline, not drawn to scale, as I'm sure you've noticed. And the bear has 500 kilograms worth of mass. So if we want to show what forces are acting upon this, we've got the force of gravity going directly downwards. We've got normal force, how it's not normally, which is normally in every other type of problem with forces. Normal force is almost always going to be straight up. However, in this case, it is angled because the fact that normal force doesn't act straight up, it acts perpendicular to the surface, so it is making a right angle here with the surface. And the last force that we have is force of friction pulling us up the ramp because the bear doesn't want to slide down, and friction between the paws and the surface is causing it to try to not slow down. Now, you'll notice that only one of these is on our standard axis. Gravity is the only force that's on here that lies on our standard horizontal vertical axis. So, the fact that normal force and friction force are unknowns and on not entirely on our axes makes it problematic. The way that we deal with this is we create a rotated frame. We've got a separate axis that we can do here, where we treat this into and out of the ramp as the new y axis, and this up and down the ramp portion is the new x axis. Okay, so that when we go to make our net force equations, our new x direction has all of the friction force and some of the gravitational force in that direction. That's equal to mass times the acceleration in that direction, and we can't say that that's 0 because we know that the bear is actually moving in that direction. We don't know how fast or whether it's accelerating or not, so we have to leave it as that. Our net force in the new y direction, however, has the normal force lying upon it and the force of gravity in that new direction, and that equals mass times the acceleration in that direction. But since we know that the polar bear is neither sinking into the hill nor jumping off of the hill, we can say that this is in fact 0. Now, if we take a look at this now, the first thing that we want to do is we want to find the normal force on the bear. Given our new equations, this should actually be fairly easy. All we have to do is find out what this new gravitational force in the y prime direction is. So let me show you quickly where that is. So if I break gravity up into its components, okay, this would be the force of gravity in the y prime direction, this would be the force of gravity in the x prime direction. We know that this angle on the inside, because of some fun geometry, is 30 degrees as well, just like the incline. And it's not too hard to picture that, because we know that if our hill was reduced down to 0 degrees, in other words, a flat line, gravity would be straight down, and so our axes would rotate until it would be straight down again, so it wouldn't be a problem in that case. We want to find this. According to some trig, our amount in the y prime direction is actually the full force of gravity times the cosine of the angle. And so force of gravity is just mass times the acceleration due to gravity, and it's cosine of 30 degrees, so that when we plug that in, we end up with 4,247.85 newtons, and that's the force of gravity into the ramp. And so according to our equation, since that is what this is, and we know that that equals 0, then we know that the normal force is an equal and opposite amount in the opposite direction, so that means that they are 4247.85 approximately newtons out of the ramp. Now we want to find the friction force. What we would do is, now that we have the normal force, we know that we have the relationship between normal force and friction force using the coefficient of friction. Right? So if we want to find this, we know that the coefficient of friction in this case is 0.2, and our normal force is 4247.85. So that means that our friction force is approximately 849.57 newtons up the ramp. Okay. Now we know the force of friction. All we need to do in order to find out what the net force is, and that would be in our x prime direction, our new x direction, all we have to do is just plug in, find out what the gravitational force is horizontally in our new horizontal direction, up and down the ramp. And so that is very similar to the new vertical, but all it is instead of using cosine, we now use sine. So when we do that, we get 500 times 9.81 times the sine of 30, which is 1/2. We end up with, in this case, 2,452.5 newtons down the ramp. And so our net force in the x prime direction is equal to 2,452.5 minus our friction force, which is 849.57, which gives us a total net force of 1602.93 newtons down the ramp. And so we can find our acceleration, which is equal to the net force divided by the mass. So we have that value divided by the 500 kilograms that the polar bear is. We get an acceleration of 3.21 approximately meters per second squared down the ramp. Very last question, we ask, okay, what is the angle that would work for this? There is a very simple equation that relates the coefficient of friction in a zero net force case to the angle, and that is the tangent of the angle must equal the coefficient of friction. And now this is the tangent of the max angle, okay, before it starts accelerating. So if we want to find out what this angle is, the angle max is the tangent inverse of the coefficient of friction, which in this case the tangent inverse of 0.2 ends up giving you an angle of 11.31 approximately degrees. And there you have it. There's the basic ramp problem. We will do more of this in class, or if you don't have me in class, then enjoy this free knowledge. Have fun and enjoy the rest of your day knowing that you know how much it takes to slide a polar bear down a ramp. Enjoy.